little bit late. So the video I just played was like a deep learning computation from last year that Amazon AWS played with this depressor, that small car. I will introduce it a little bit later. So the thing we're going to talk about today is RN, recurrent neural network. So probably we don't have too much time to run the Jupyter notebooks, but I hope I can, but I need to access my laptop first. So let's just finish this, and we'll see what else we can do. And before we start with, and this is outline for today, so the sequential model and the language model, and also the generalized RN architecture, the GRU, LSNTM, and some ideas for more deeper RNs and the bidirectional RNs. And before I start with RN, I have some kind of logistic thing that, can I ask, have anyone successfully set up your AWS? Oh, I saw a bunch of hands. I'm so excited now. Okay, but I haven't. Because this morning, I have some issue with access to the remote VPN server, and I don't know, every 5 minutes it came out. Probably that's the reason that I cannot access my gate this morning. But so if you haven't set it up, maybe you choose the wrong reason. And some people claim to me that the Singapore reason doesn't work because they have limited servers, and if all of us access there, they don't have that too much residuals for us. So probably you can try the other, like Tokyo, like Sydney, maybe try different servers for your limit increase. And the second most important thing is don't forget to stop your instance if you don't want to train it anymore. Or if you are still leave it running, it will cost you a large amount of money. So what you do, you just right-click on your instance, and you click the stop, and it will stop it. Even stop will charge you a little bit because you still have your data there, and AWS is still holding everything, your environment there, but it won't charge you a lot since everyone has 100 credits, so it should be enough for you. And the difference between stopping and terminating is that stopping, you will still have your server there. You can go back, restart it. But when you terminate it, you throw it out. You don't want it to come back. And next time you need to set up, pipe install everything, and load your data. So how do you check your bill of AWS? So you just go to the search box, enter the building there, and they will go to click that building, and you will see that it should be 0, which is ideal, but probably you will have some dollars of charges. And if you forgot to, never mind. So the next is AWS depressor, and this is a small tiny car that people now run it to do the autonomous driving, because we cannot buy a real car and run it on the road, or the police will take us to the jail. So we have this small toy models, and everyone runs it. Everyone train their reinforcement learning models and trying to play within that computation that in the video I just played. So you can access this depressor simulator, which is online from remote offer. You can just access to that AWS on console and to train your models there and to evaluate them. And then you can even remove to play with your small car. So it's pretty virtual computation. You don't need to be physical there to join that computation. But if you remote access it and evaluate your models, you'll be fine. And I believe the credit and the best credit will be you will win a car or something like this. Yeah, so join it if you want. I believe that now the competition is in Shanghai, and the leaderboard is all on site. So I'm going to upload this slides later to my repo because there's some issue. But you will see that there are links. You can just click it and access it, and maybe there's some really helpful link for you to build your first models and how to improve your models. So they have their instruction there, especially if you want to train using reinforcement learning. And here's a different topic. So some students asked me, let me recommend some courses on textbooks some results for machine learning, deep learning. So here are some courses that I took that I feel like it's pretty useful, and most of them are from UC Berkeley. So probably I'm a little bit biased for Berkeley, don't blame me, but they are really good course. So the first one is Introduction to Deep Learning. I was also the TA for this course, and it's like introductory to medium level. If you're really advanced, don't take it. And it has like all the lecture videos, slides, and our homework, even the midterm and midterm solution out there. So if you're interested, you can go there. If you're interested into special topic, for example, natural language processing, we have like special topic for that. If you're interested into attention, BERT, we have like this quite new lectures there. So they're all available free online. And the second one, if you're interested in like the traditional machine learning, Berkeley also has this CS 189 course, which is Introduction to Machine Learning. And it's taught every semester at Berkeley, and all the past year's lecture, video, slides, homework are online. So, but this work have lots of math. So if you really want to dig into math, do some proof, have a deep understanding, go for that. And the third one is the foundation of data science, which kind of introduction level course, like from the scratch, like how do you deal with the data. It's like a more broad than the machine learning models, so it includes more statistics. And it's also free online with its lecture videos. And remember, like Michael Jordan, who is really famous for machine learning, he's going to talk about the next semester's course for the foundation of data science, which will be super popular, super crowded. And last but not least, if you really want to learn some advanced course, I highly recommend this deep reinforcement learning course, which is pretty popular, taught by Berkeley professor called Sagarita Wen. And he's a really great lecturer and a researcher. And it's like an advanced level of reinforcement learning. It has all the videos online for every semester, or maybe every year, because I only offer it once a year. And also slides, homework online. But this course is pretty hard to debug. So next slide, some GitHub and some textbook. So the first textbook is Dive into Deep Learning, which also called D2L, which is like most of the resources from the lectures are coming from this book. And also, if you're really into CV, Gulang CV, it's a great toolkit for you because it provides some implemented state-of-art trained models that you can just grab it and fine-tuning yourself, apply on your data set. And we also have Gulang NLP, definitely it's an NLP model. It also have all the state-of-art natural processing models there, especially nowadays the BERT and XNet coming up. We have already I think they spent like a week to train the whole BERT and put it there. So if you don't have that much GPU, I remember we spent like 64 instances, I forgot last time, but it's a lot. Like we got an email from the EC2 team, they said like, you guys run a lot of AWS like instance, what are you doing there? Like we trained it for a week for this BERT. So you can just grab it and use it. And we also have Gulang TS. So if you're really interested into time series, and that would be a great toolkit. It just released actually 2 months ago, which is pretty new, but it's pretty powerful for deep learning on time series, and which is a quite important field now. And also, last but not least, there is like an online discussion forum called Maxent Online Discussion. And it's like online portal to discuss like any deep learning, machine learning. If you have any issue, you can ask online, and there will be professional, like there'll be like the community helping you answer your question. For example, like this is kind of the interface for the online forum. You will see that people are asking about naive Bayes classification, or you can say the installation is pretty popular. Lots of people asking about why they cannot install some maybe package. And there's like softmax regression issue. So any issue with either math or models or like coding, you can ask it online. And this is a link for that, the discuss.mx.io. And the next is a detailed textbook. Actually, my mentor is one of the authors for that. That's one of the reasons I recommend it. Why I recommend it? if you are really like a starter for deep learning, it's really good books because it's really described from a not that massive field, so you don't need to understand that much of a math because like all of them are coming from a computer science background. They are not like me, coming from a statistical background. So they're kind of really practical, like engineers and the researchers, and they write these books. So has Alex Smola, he's my mentor back in Berkeley. And last but not least, you can reach me at my email, but I cannot access it because I'm kicking out by my VPN now. So you can still send to me. Maybe I will reply it in 10 days. Sorry about that. And so if you have some further cooperation with me, for example, if you're a professor or you're a graduate student, you want to teach a deep learning course at your school, so we're definitely welcome for you to offer using our textbook. And you just need to send us an email, and we can provide you all the previous homework, all the solution, which is not released publicly. And also if you want to translate to different language, which will be really helpful for us. Because now we only have like, I think, a Chinese version, English version, and also Korean version, Japanese version. I believe they have German version translated now. But if you guys are welcome for like an entire version, that would be super helpful. All right? Building the community. And last but not least, if you are complaining about some errors about the code, if there's some bugs for installation, and if it's unclear for you to understand some concept, you can just also email me, or you can just also post on the forum, and there will someone answer and figure it out. So any questions for all the previous things that I just flipped through? Okay, let's start with today's topic. I will start with the dependent random variables. So our lecture before today, we all talking about some independent random variables. So why is that? So remember, like all the models we're talking about previously, no matter whether it's like MLP models or it's like convolutional neural network models, we're trying to collect those observation pairs pair by pair. We don't consider their correlation with each other. It's like they're all independent, like kind of independent of each other. And we estimate the y given this x, and we predict its probabilities of y given x, which is our ideal model. And some example, image classification, object reduction, etc. But of them, the order for the data set, it doesn't matter. So each data come in, they're unique, they don't depend on each other. But let's see some interesting pictures. So this is pictures written by a paper 10 years ago by Korean. And it's like kind of a prediction for the Netflix movie scores rating. You can say on the x-axis, it's like the days, how many days it's running for Netflix. And the y-axis is a mean score for the movie's rating. You can see there's like a huge jump here in about like 1,500 days. And you wonder what happened to Netflix. Is there like recommendation models suddenly got better? Or maybe they just switched to different user group? So actually, none of them. It's because at this day, Netflix changed its labeling rating system. So previously, they like have their bad movie as it's bad, or just like it's a bad movie. But now the one score rating, it's like I hate this movie. And when the audience say that, probably it's a bad movie, but maybe I don't really hate it. So they won't give a 1, they will just give a 2. And that's why like you will see the big jump here that I don't think anyone is going to give a 1 for this kind of a rating scale. So that's the interesting jump. Another pictures, similar thing. We also have the axis as the days, y-axis as a mean score. You will see like this is like the rating by the moving age. You will see that as the movie got older and older, you will have like higher mean scores. Anyone know why is that? Okay, think about if you are watching movies. No. And either you're going to watch recent movies, like pretty new, like on all the news now, and your friends are talking about it, you definitely want to watch it. Or if you are so bored, you're probably going to watch an old movie. But that old movie should not be bad, right? It should be a good movie. Like someone else have already watched it, and it's like rating on 4 and 5 there. So as time goes, people tend to watch more good movies than bad movies. So you will see there's a distribution shift skewed to the right on your better scores. And that's why even though you will say it's moving, get older and older, it's like the average is towards a better scores. Because people tend to watch, they prefer to watch more good movies. Yeah. So we also call it selection bias here, which like user try to select the better one. And another interesting pictures, we have the average life certification for German women. It seems that they are pretty happy during the first year, actually the 0 years of their marriage. I don't know what happened for the German male. Maybe Craig know more about that. But I think that they feel not that happy anymore after they got married longer. What's that? Maybe it's like because it's pretty old survey, it's like 2006, I believe. So I believe it's a universal phenomenon. It's like a researcher done by a German researcher. So I'm sorry for that. Another interesting, it's not German anymore. It's like the life certification in China has the average real income rise by 215%, pretty amazing, for the past 10 years. And you can see like more people are richer, but they are not happier or maybe more dissatisfied with themselves or maybe their neighbors. So, without further ado, there are so many cases that the data are not identical, independent, distributed with each other. So like the quarterly earning, like the Fed rate cut, or like for Amazon, we have the inventory, the Prime Day, the Christmas, those events, which makes those data will not be like identically distributed, identical independent distributed, but they probably will be sequential data. And that's why we're going to talk about sequence model first. So what is a sequence model? We have this like x1 to xt, which are each time step, you can say, and we should follow some probability distribution. And if we use the Bayes rule, you can try to expand them to the end, one by hand, and you will see this like blue dot circling from the fourth time because we're trying to model this, and we assume that on the last time step, on the x big T will depend on all the previous time step. And that's like the basic for series model, sequence models, no assumption now. We can do some autoregressive model for that. For example, we can have some function that we're trying to model it with using like autoregressive. So we can go with two ways. So the first one is like we can have this Markov assumptions, which you will have still the same picture, but we assume that the current time step only depends on the past maybe tau time step. For example, like today I'm going to like be here for the MLRS, maybe only depends on the past months, like my email with like all the other researchers, like all the 30 days like of my schedule. It won't depend on like any days before that. So that's the basic idea. And what we can do, we can just remove all the other term and just keep this tau term for the from the t minus tau to the t minus 1, and using that to model the current, like trying to predict the x t hat. And what model can we use? We can use like, for example, MLP, the basic dense layer, we're trying to predict because we have this big set of data, like we only have these tau features in this model. And another plan is like we can go to some latent variable models. So what is the latent variable models? We have this kind of green dot H here. So assume that it's a hidden state there that we cannot watch it ourselves, but it exists. And we have some two assumption formulas. Like first is the probabilities of HT, which is the probability of the hidden state for the current time step, will only depends on the hidden state for the past time step and the last input. And the second assumption, which is the probabilities of the current output X, which is the next, like the thing will happen next, will depends on the current hidden state and the past input. So it may be a little bit abstract here. Let me give you an example. So now I'm like presenting here, like the words coming from my mouth and coming to your ears. And then there will be some hidden state in your brain. And you're trying to using the past experience, like past words that I already said, which is all the H minus T, which is the past hidden state, and trying to infer in your brains to the new hidden state. And what you are trying to do, you're trying to using the new hidden state and the past words that I just said, and to predict the next word is going to come in from my mouth. And that's like the idea. What happened? Any question? Yes, good question. Okay, I can repeat. Yes.
Oh, okay. So my question is, I'm thinking about a latent variable about the x step 0, and then how do you find the h initial state?
That's a good question. So the question is like, how do we define the x0 and h0, right? So h0, definitely we are going to initialize like all the other ways. We'll probably initialize with standard normal distribution, no, normal distribution with mean 0 or standard deviation with 0.1 as like initial prior. So and then we can adjust it when we train it. But for x0, it's like we're thinking about as an input. For example, in the next word prediction, we have the input coming from word by word, and then the x0 will be the first word, and they're trying to output the x1, which is the second word, and it will be the output. But then the second word will also come in as an input for the x1. Yeah. Good question. Any other question? About like plan A, plan B, the Markov, and the latent variable. Okay. Oh, I haven't finished. Okay. So latent state H. This H will be summarized for all the past information. So you can say like there is like HT here. It can be function for all the fx1 to xt, which also equals to like fht minus 1 and xt minus 1. Why is that? Because like if you plug like t minus 1 here, it will also like equals to from x1 to x2. So you can just derive it by yourself from 0. But which save us a lot of parameter. We don't need to write everything down. So for text processing, so how do we compare text processing to, for example, the image processing we just talked about yesterday? So for image processing, we have this like picture in 2D, which is coming from within its batch size. We have like the width, we have the height, we have the RGB channel. And for NLP problem, when the text come in, you have a batch size, and you have like a number of sentences. So think about that. I just heard that yesterday that Thai don't have like any symbol in the sentence, right? So you don't have like space, which like pretty amazing for me. How do you guys really cut your sentence? But in a traditional English sentence, we do have this comma, this period. So we assume that for each sentence, there are like some words we combine together, and it will be the sentence length. So here, the sentence length cannot be a fixed number, so it'll be a variable number. Maybe it can be like 10-word sentence, or it can be like a 100-word sentence, etc. So what are we doing with those sentences? We do some tokenization. For example, if I have the sentence, deep learning is fun, we tokenize to 4 words. With word level tokenizing, like deep learning is fun, period. We can also do chapterized encoding. We can like split to like deep, E, E, P, etc. For each chapter. We can also do the bad pair encoding, but there's a golden lock zones for that. And vocabulary, yes. So this is like the common token with their frequency. So in English, maybe lots of words are pretty not that common, and maybe in a large corpus, they don't happen a lot of time. Maybe they only happen 10 times. And if it's a large corpus and the word happen less than 10 times, probably we're going to remove it. And you can see on the right-hand side, this graph is kind of the word frequency happen in some of the corpus. Like as your token coming up, you will see the frequency will coming down, like which is your threshold. So how do we do some like mini-batch generalization for a text document? So the first row will be our sentence coming in. And think about that now we are trying to do the chapter level split. So we have like this 5 chapter as a group. So we split every 5 chapters include the space. And then we slide this window to the right and we're trying to generate this mini batch. So like you can think about each of this cell will be X features. Notebook, let's go ahead. So before I talk about that, any questions? Okay, so these 2 topics are pretty similar. The next topic is language model. So for the first sentence, we have the deep learning is fun. There's 5 tokens coming in. How do we model them? How do we model the probabilities of this sentence happening in a corpus or etc.? So we can use in the famous Bayes rule. We have the probability of deep, what you call times the probability of learning given deep, times etc., which is expanded using the above formula here, which means that as long as we have each of this like conditional probabilities and also the probabilities of the first words, then we can have everything for the probabilities for the whole sentence. So this is the base assumptions. And common NLP task. So how many of you heard BERT before? Oh, great, a lot. So why BERT is a pretty amazing model? Because it's broken lots of like fundamental NLP tasks. So it's not only broken one task, accuracy or error record. It's broken all of them, most of them. So the fundamental tasks for NLP, like name identity recognition, like for a sentence, whether this is an object, this is an organization, this is a place, this is a location, etc. Also, part of speech tagging, machine translation, question answering, and summarizations, etc. Before that, any question? Okay. So now let's come to deep dive into the models. So why we call it recurrent neural network? So this is a basic structure for recurrent neural network. You will see like there's like a small cell, it's like the neuron, and there like input coming in, output comes out, and there is like a hidden state in this rows that keep transferring information from one cell to another. And this is the basic architecture for recurrent neural network. For example, you will see that there's like input from time step t minus 1 to time step t to next time step t plus 1, and you will have the output coming out. And in each of the big square here, you will have the activity function as probably sigmund or ReLU, etc. within the hidden states. So what are the formula here? Yeah. So here's the formula for the basic recurrent neural network. You will see this hidden state is some activation of the weights of the previous hidden states and time plus the weight of the previous xt minus 1 and then plus its bias. So this 2W, you see like the WHH and WHX, they're initialized at the first like standard normal distribution, and they're initialized independently with each other, and this WHH is only applied on the previous hidden state, and this WHS is only applied on the previous time step. And we get this current hidden state, which is HT, coming here. So we can output it here using new weights, which is WHO, and this also an independent weight that we initialized at the first time step. And also you have the bias there. And then you will have the output and the like time step T. So compare the RNN with a two-layer MLP. It's kind of similar. Besides, you have the left-hand side on the yellow box, you have this hidden state. All the other thing kind of the similar. So let me give you a specific example using next word prediction of how RNN work. For example, you have the input of like time machine by age as your each time step coming in. So at the time step 1, you have the and you put it into your hidden state, which has already been initialized before, and then calculate the hidden state H1, and it will give you the output O1. And the output O1, we expect it to be similar or close to time because this is a next word prediction, and we want the next word to be time, which is the next input. So you have the time here. And now, what are we going to do? Yeah. I want to draw it here, but I can't. Oh, sorry. Okay, it's too quick. So what I'm going to do, the next step, the hidden state H1 will tell the hidden state H2, oh, I learned that previously there's a the, and I predict time. So the hidden state 2, they will know that, okay, there's a new time coming in, and the previous hidden state coming in, and then I will predict the output O2, which will be the machine, and which is the next word, and which this hidden state trying to learn the next word will be a machine. Similarly, for the rest time step, should I come to here? Oh, okay, yeah, this is better. Okay, so the next step, you will continue learning, continue updating your hidden state yourself, and continue predict the next words. So you will say word is kind of not a number. How do we use model to train it? And that's the trick that we do the one-hot encoding. So for each given word, we have for example, we have 100 word corpus, and each of the words we just assume that they only appear once, and we can one-hot encoding them to turn them to be 100 element vectors with their indices only be 1 and all the other elements be 0. So for example, the first element of this dictionary, the first word, for example, the coming in, and only the zeroth element here will be 1, all the other element will be 0. And this vector length will equals to the length of the vocabulary, which is your dictionary. So in this way, we can map each of the words independently to some vectors. Standing there, then we can train them. So here's the generalized mechanism for RNN hidden states. You have the input, which has a vector, which of the RD dimension, and this D will equals to your vocabulary size or your word vector size, 300 dimension or 50 dimension. And you will have your hidden states from H1 to HT, which belongs to some hidden states of dimension RH. And we assume that HT will be some function of the previous HT minus 1 and the XT. And then your output the new words, maybe it can be the next word, then this P will be equals to D. And if it's the next word, it's not the next word prediction. If it's not, it's just like some classification task, and then your output will be equals to the number of the class. And what we're going to do, we're trying to apply some softmax regression for this OT, which each of them will be representative for some confidence scores of, for this time step T, what kind of token it should be. Like for the next word prediction, like if the came in, like how confident the model is, the next word will be the time. And for each of the words in our dictionary, they will get this kind of probability. This is why you will see this like OTG. The T is for the current time step, J is for each of the indices in the dictionary, like all the words. And so remember this Rn, we have a long chain of dependency. So have this like circle and the edge all around from the past time step. So when we do the back propagation, we backprop from the last time step to the front. Maybe it's too far away, and maybe we can get some gradient vanish and gradient explosion. Remember yesterday I talked about gradient vanish. If you times like 0.8 100 times, it will be a super small number. So that's the same idea. And so how should we? What's the trick can we do? So you can have some like the theta here. And you have the gradient, which is a G. And you get some matrix applying your gradient. For example, you can have like the L2 norm. And you use the L2 norm and divide it by this G. So you will get the direction of this gradient. But you want to keep the norm to be some value, which then you can keep with this theta. So this G will be either the mean for this one and the theta over J's norm times the G's, which keeps the direction. And this is try to rescale the gradient to at most some theta. Rn notebook. Okay, any question for Rn architecture? Like, I believe I talk a little bit quick because I'm worried about there's no time. Okay. So the next model we're going to talk about is called GRU, Gated Recurrent Unit. It's like one of the special model for Rn. And why special? So think about that when your eyes, like your visual system is looking at those pictures, you have 5 cat and white rat inside of you, probably most of us will pay more attention to this fat rat. We don't care about the other cat. So that's like some phenomenon that we can extract from a visual system. Can we apply this kind of motivation on the model for Rn? And the idea here we got is we need some mechanism to pay attention. Like, for example, if in an early observation, there's some like highly significant predictions that happen. Like, for example, I know that in chi-squared, you have your subjective, so it happened at the first time. You're talking about using that, the, it, whatever, and to reference that, which is happening a long times ago. And we probably need the Rn model to memorize it and have some cell to memorize it before we get in too far from that specific words. So that's the basic idea. We need some gate to keeping update that whether we should still store this like this important value or we should update with some new important value. And the second one is we probably also need some like forget gate. For example, in like the English sentence, there's some logical break between two sentences. Like there might be some translation between chapters, like different chapters, and you will see there's like a bear market and a bull market for like the securities trading. So that's like some common phenomenon that we probably need some forget date, like reset everything when it's coming to the next chapter. So that's the basic intuition for GRU. You can see on the left-hand side is a traditional Rn neural network, which have these 2 lines, which is pretty amazing. And then on your right-hand side, it's like called GRU, the gated recurrent unit, which you have like 3 more rows here. What are they? They are like the reset gate here and the update gate here. They also have a hidden memory cell, which is this ace tilde. And I will explain it one by one. So the first part for the GRU is that you have 2 new gates. One is called the reset gate. The other is the update gate, which we call the RT and ZT. And each of them will initialize their own weights, which you can see this like x times to WXR, and there's like WXD. So this weights, the first weight is for the reset gate only, and second weight is for the update gate only. And similarly, for the hidden state, we also initialize their own weights for both reset gate and update gate. Besides, we also initialize the bias. So similarly to the traditional RN, we initialize everything and time with the input and the past hidden state. And then we apply some sigma function or any other activation function to get this current gate value. So what is the next step? We also have this H tilde. We call it a candidate hidden state. So why is a candidate one? It's not a real one? Because it only be used to calculate for the next step. And how do we calculate this candidate? We will use the reset gate and to reset the previous hidden state. So it's like if there's some value from previous state, whether we should reset it, if maybe it's previous chapter, we'll just reset it. So we use like RT O dot with HT minus 1. And also time with the WHH, which is just for this candidate gate. And we also use like initialize this like WXH, which is kind of the normal ways that we also initialize independently compared with the other ways, which is just apply on the new input XT. So we have this 2 term, we plus a bias, and we apply the tangent function on it, hyperbolic tangent. Why is that? You can just think that previously we all applied like sigma function here, and now we applied hyperbolic tangent. Why is that? You can say reset gate is like whether I should reset something is like either 0 or 1 question, right? And also update is like 0 and 1 question. So sigma function is trying to map every value. Remember, like the function is to 0 and 1. So any value between 0 and 1. It's like kind of probability whether I should update it, whether I should forget it. But for this candidate scale, we use hyperbolic tangent. It will be mapped to -1 and 1. And when we have there, it doesn't matter whether it's like a minus number. It doesn't mean any confidence. That's why we apply hyperbolic tangents to have some kind of range. We can have some opposite value. Maybe sometimes the hidden state can have some really opposite influence. And why we have this hidden state? It will be used to update the new hidden state. So how do we update it? Remember, we have this update gate, and which may contain some previous state really important value. And we use this update gate and times with the previous hidden state. And we also plus that 1 minus update gate, O dot with the H tilde. And that is the new hidden state that we just coming out from this cell. You can see the hidden state coming in horizontally, and there's an input coming in from the bottom of here of the cell. And you do a bunch of math calculation, and you get the new hidden state. But we haven't done yet. Yeah. Okay. Here's a whole summary. How do we update each of the gate? But remember, after you update each of the gate, you still need to output something. So using the new hidden state. Any question for GRU, please?
There's a lot going on in that picture.
So this picture?
Yeah. Could you explain what's the 1 minus there doing and what's the multiply doing?
That's a good question. Okay, so here's a basic whole picture that we see. In this picture, we have initialized, I think, 1, 2, 3, 4, 5, 6 different weights. And each of the weights will be applied for, each of the 2 weights will be applied for each of the 3 gates here. Why is 2 for them? Because 1 for the input, the other for the hidden state. As you can see, this is update per 1 time step. And you will have this bottom layer, I don't know whether you guys can see it. It's like you have input for this time step coming in. And what are we going to do? The first time step, we update the reset gate, and we'll try to figure out whether we need to reset or not. And second time step, we have this update gate. We're trying to understand whether there's something in the memory cell, should we update or not. And we also need to calculate this candidate hidden state. You can think about it as some kind of memory, which can be -1 to 1. Maybe why we need to memorize that would be -1. For example, if you say some like sentiment classification, you say like I love someone or I hate someone, they're probably like 2 scales. We don't want to map all of them to be 0 and 1. That's why I kind of keep them to -1 and 1 and to keep this sentiment. So there's not that much intuition that why people like using y-1. I'm still wondering that. I believe like this state t is between 0 and 1. So we can use -1 to get another probability. So it will be add up to 1. But I'm not quite sure whether they're doing it this way. Yeah.
I guess I'm confused because I understand the reset part, the R part. You are trying to forget the old hidden state by multiplying like 0 to it, but also in the update part, you kind of also let it pass through by the top path there. So
yes.
So it's kind of doing the opposite thing, right? Because
actually no. So. You can think about that. So this ht-1 contains all the previous memory that you already saved from x1 to xt-1. And then you apply this update gate to say that whether you want to update or not. But you also have this h tilde that you probably have some important memory there that which you pay attention to. And that's why you have this zt, which you apply some weights to all the previous state memory, xi to xt. You also have this memory that you apply a higher weight to just this word. I believe that's kind of intuition.
What's the difference between h and h tilde again? There's the h and the candidate hidden state.
Yeah, good question. So candidate hidden state is calculated within this union, but ht-1 is coming from the previous state union. So previously there's also like some square like this. It generates some ht, which you can think about ht-1. It will be passing through some edge, maybe passing through like your neurons and through your axon, and then to the next neurons, dendrite, it will come in, and you will calculate, I have this hidden state, which is kind of information saving from before. Yeah.
So my understanding is that you are trying to weight how much of the old state you are going to consider, and also how much of the candidate state. So you're trying to give importance to either one of them and combine into the new state.
Yeah, you can think of it this way. That's like an intuition for that. Like no one really can prove it.
But what does candidate hidden state actually mean in terms of the NLP problem? What are the candidates in this case?
So I guess when people design this architecture, they are lack of words, and so they are like all the words in their hand, like hidden state. So I feel like maybe you should give them a better word than it's like candidate, I would say. But the similar thing in LSTM, which we're going to talk about next, called memory cell, because they're doing the same thing. You can just think of it as a memory cell.
Okay, thank you.
Yeah.
I'm not quite sure if I'm right or wrong. What is the range of the h to the t? Is it -1 to 1, right?
That's a good question.
Because is it tan H?
I don't think it will be between -1 and 1. Even though, I think if we are initialize this hidden state with some mean of 0, and then we continue process like h tilde between -1 and 1, then probably we can end up with some number bigger. But it should be between the -1 and 1. Yeah.
So is it the vector that determine the, it seems like to me is determine whether we should reset or update the HT or not, right? For the H to the T, right?
Mm-hmm. Yeah.
But for the real HT is the ZT, right? It's, to me, it's quite confusing for...
Which line?
Yeah. Because for the ZT, it seems like it's quite similar to the HT minus 1. It's the last step.
So ZT is similar to HT minus 1? You mean this guy is similar to this guy here?
Yeah.
It's like you can think about like all the cell in your gate is like you train yourself. It's not some information. It's not some truth. But the hidden state contains some truth, and the input contains some truth. That's probably some difference. Yeah, and you have your weights, which is kind of your belief, your bias, apply on the truth.
Maybe to me it's like the end result of the cells is the H minus T is the end result of the past cell, right? But for the current cell is the HT, right? But for the HT, the inside this cell is the ZT. But for the ZT, we have to to determine, we have to forget or update it before. But actually, we have to pass the input and the HT into the activation function, but that thing is the CT. Am I right?
I'm pretty sure that your first part is right, but I'm not quite following your last two sentences. So are you confusing with that? Like, why we have this ZT and this HT?
Yeah, it's pretty confusing for like.
Okay, so you can think about like RT and ZT as two gates. So they're kind of some matrix there. They're not some information. They're something like to measure whether we should keep the previous information and throw it out. And HTs keep all the previous information, and also the new input is the information coming in. And we want to train by passing all the information. We want to tune our gate to be not that high, not that low, to be some adjustable range. Yeah.
Maybe it have to take some time to.
Yeah, probably don't need to understand often, because originally when people do it, they just train and it work, and no one really prove it. Don't laugh about it. It's like it's really hard to prove like what is happening in your cell, in your brain. It's a hard thing. If you can prove it, then you will get a Nobel Prize, I believe. Okay. And next thing is the long short-term memory, which you can see. Like on your left-hand side, probably this guy have like a short-term, which like only 7 days memory. And on your right-hand side, probably this guy have like really long-term memory. And we don't want to both, but we want to keep their both specificity. So what's the difference between GRU and LSTM? You will see like this formula is growing larger now. On your left-hand side, it's like the GRU algorithm we just talking about. On the RT, ZT, the reset gate, the update gate. And on your right-hand side, you have 3 more gates. You have the forget gate here, you have the input gate here, you have the output gate here, which is input gate, forget gate, output gate. Also, you have this memory cell, which we call it memory now, not hidden state. I believe researchers are different, right? They have different priors in their brain. They're just using different words, but they're kind of similar thing. So you can think about it as a memory state came in, and you have a candidate memory cell, which is T delta, and you update it similarly. So that's a basic LSTM algorithm. You just have one more gate, but you have like kind of different algorithm to process them. So let's look at them one by one. Okay, so what are the first 3 gates doing here? You will see that each of the gates, like previous GRUs, update gates, and reset gate, we also have this 6 different weights for both input and the previous hidden state. We initialize independently weights and bias. Pretty traditional, like the previously traditional RNN cells to calculate update every gate. And now you have a new thing. So besides the previous hidden states, you want to keep the previous hidden states into some candidate memory cells. So you probably want to memory it, but you don't want to tell the next cell that you want to memory it. So you call it candidate. You keep it in your cell. You just memory yourself. You don't tell the next cell. And what's the formula? You initialize new weights, WXC and WHC. The times with the input, the hidden states, and plus your bias. Similarly, you have the hyperbolic tangent function here to map that memory to be -1 and 1. And the next thing you're going to do, you want to evaluate whether your memory is wrong or true or wrong for the current candidate memory. So what are you going to do? You apply the forget gate for all the previous memory. So maybe you memory a lot of things, and you want to decide whether you want to forget. Also, you have the current new candidate memory, and you want to evaluate whether the current memory should I memory or not, and pass it to the next cell. So that's why you apply your input gate, which is like your memory just from this input, and your input is just to determine whether you want to pass on the current candidate memories or not. So you will have like 2 rows. The bottom row is from the previous hidden state, HT-1, to the new hidden state, HT. You also have the upper rows, which is a memory row, which is a memory cell row, which is say T+1, and you pass it, do some multiplication, update it, and to the new memory. So how do you get your new hidden state? You want to decide, probably I want to output my memory to and pass it to the hidden state. Then how do I decide whether I want to output or not? You have this output gate, right? So you dot that output gate to the candidate memory cell, to the memory cell, sorry, for that what you just calculate above. So that's the whole 6 formula, which is a lot of math, but I believe LSTM for me is have more intuition, more like motivations to derive the functions. And interesting is that like LSTM was derived by I believe some German researchers like 20 years ago. It's a pretty long time ago. But GRU, which have lower gate, it's like 5 years ago. Some researchers just derived it. I don't know, maybe they just suddenly read their papers. Any question for LSTM? Yes.
I've seen your slide. One of your slide you mentioned memory gate, right? But where is memory gate in this in this chart?
You mean the memory cell or something?
Oh yeah, memory cell.
Okay, so the memory is probably not a cell. You can think about it as some kind of information, the state you want to save. So it's like here. So it's passing from the previous neuron and to the new, like this cell. And you also want to keep it updated in this new function by your new candidate memory cell, and you pass it through to the next step. So that's why you have two rows here passing to the next time step.
And the gate that we make a decision to memorize or not is at the forget gate or where
Exactly. All the gate here is trying to be the judge to say like whether the information coming in, what kind of like algorithm I want to do, whether I want to sort it out, whether I want to keep it. Yes. To make a decision, what will be the output for the CT and HT, like the whole algorithm will work together. Okay, I probably run a little bit late, but I want to finish it. If you guys are good with like 10 more minutes, so I can finish my lecture. Yes, please. Yes, the OT is the OT is not. The OT is just for the output gate. Then you will apply some more function, if it can be a sigma function or can be any other function to do the classification. To classify like the next word you are going to output. So apply on this hidden state.
But I don't see it in the picture.
Yeah.
Which arrow would lead to the answer?
Probably I would say there will be another arrow here. Drop it. You will see the input coming in, output coming out.
Because I don't know like how do you, what's the formula for computing the next sequence, the next word in the sequence? Does it depend on C only or both C and H?
Actually, it won't depend on C. It will depend on H and input. So it will be the same as the traditional RN. Yes, good question. I should put it here. I don't want to put so many formula to intermediate you guys.
There's a lot going on there.
Okay, good question.
Thank you.
Okay, I will finish quickly. So I have two more things, which are just ideas to talk about. And the first is deep RN. So now all the RN layers we're talking about is only one layers, right? We have like horizontal lines. And you will see different types of RN. You can have one-to-one, one-to-many, many-to-one, many-to-many for different type of sequence. For example, for a question-answer sequence, maybe the question will come up one by one itself, and then it will, until the question mark, it will be how start answer, and then you will see that like there's a split here. And this is RN cell, as your question is like observation update is in the last row. So the previous for all apply for GRU and LSTM. So we probably want to do more things. So we have this output layer, but probably we are not really satisfied with them. Can we do more? Then what do you want to do? It's one can go deeper. So you can say from the first layer, which is a kind of RN's flow, and each of them will have the output layer here. And we can take the output as the input for the next layer. And stack them on each other, we can derive a deeper RN. That's a pretty simple idea. Okay, so here's like some generalization function. So on the top, you will see this is a function for the shallow RN, and on the bottom, there are like deeper RN. You have like this like index 1 to index j, which means each of the layers hidden states. And you update them one by one. And the next idea I'm going to talk about, by the way, any question about the deep RN? Okay. And the bidirectional RN, which is pretty important. So I have 3 sentences here. The first one, if someone can volunteer to fill for me, that would be great. The first one is I am something. Second is I am space very hungry. This should be a period here. Third one is I am very hungry. I could eat half a big. So what of the adjectives you want to fill here? Any volunteer? Yeah, exactly. So the first one is I am hungry, to keep them consistent. The second one and third one is a little bit tricky. The second one you can put I am super hungry. I'm very hungry. I'm very hungry. Or I'm not very hungry. So they're totally towards different direction. But for the third one, you will definitely know it won't be a not, because I can eat half a pig. So this is kind of the sample answer. It won't be the true answer. So hungry, not very. But you can compare from the second to the third. Like the second, you are kind of ambiguous that whether you should fill a very or you should fill or not. But the third one, you're definitely pretty sure that it's a very here. So that's why we want this bidirectional RN. Remember, previously we read it one by one as from I am very to predict the next word, but we don't know the future information. But now if we do bidirectional, can we hold this information for pigs and put it back? Then probably I know that that word will definitely be very. So that's a basic idea for bidirectional RN. Yeah. So here's a kind of a diagram. If you ignore this second line, it will be exactly the same as the previous traditional RN. You have your input coming in, you have your hidden state passing to the next hidden state, and then you have this arrow here generate your output. So this is like traditional RN, like forwarding. Now the bidirectional RN is trying to backward, using a different direction from the end to the start. So we have this new row, which exactly have the same functionality initialized here at HT. And so you have your new information passing through this arrow, and you generate your output step by step. And you propagate HT, transfer back to HT-1 until H1. So here's a summary. I think I finished it only 5 minutes ago, right? Okay. Any question for binary, RN, bidirectional RN, deep RN, etc.? Okay, great. So thank you for listening to me the super long, super messy lecture for the past 3 days. I'm super sorry that I didn't run the Jupyter notebook. I really want to show you guys it's super powerful, because if you really want to do a hand-on deep learning, you don't really want to know the theory. You want to be practical, and you need to write some code. You need to debug. After you debug for maybe like 100 days, you will suddenly know, wow, I understand it now. So do me a favor if you can install it and try to run the Jupyter notebook, because I know that I might have some bugs. And if you can help me find some bugs, that will be wonderful. Okay. Yes, I will upload the slides on my GitHub. I think everyone know it. There's some issue with my Git now, but I will definitely upload it. Today's slides. And all the notebook are online within that RN folder. So you can try it yourself.